All right, here we are again. So we have, we're not quite done with chapter 1b, where we're going to do logarithmic functions. And we're going to see that quite a bit throughout the course, logarithms and exponential functions. So, but you may have seen some of this before, but I think it's an excellent idea to review it. And then when we get into part 1c, we'll be doing something a little different. Part 1c is our overview of trig functions. And again, it's one of those things where I'm sure you've seen much of this before, but it's probably been a while. And so anyway, we'll go through that. Now, if time permits, maybe we'll take a peek at chapter 2, or 2a at least, which is our introduction to limits. Limits are important because they form the foundation for what follows. You'll see that most of the course is based on the concept of derivatives, which are defined in terms of limits. So the limits themselves are important, but the most important part of this is that it gives us a good background, so we'll have a better understanding of what limits are when we, derivatives are when we finally introduce them. So, all right, let's get back to 1b and just wrap up our discussion about logarithmic functions. So just quickly to review, so log is defined from an exponential function. In other words, if we start out by saying that y is 10 to the third power, which in turn equals 1,000, what you can do is rewrite this as log base 10 of 1,000 is 3. So in other words, the base tells me that this is what I'm going to raise to the exponent 3 to come out with the value 1,000. So these two statements are equivalent to each other. They're just alternative ways of approaching the same information. So let's just look at a few quick examples to remind ourselves how this works again. For example, here, the log to base 3 of 9 is 2 because of the fact that 3 squared is 9. Okay, so remember how this works. Here's the base, 3. It's raised to this power to come up with 9. And equivalently, since 2 cubed is equal to 8, that tells me that log base 2 of 8 is equal to 3. And again, that simply tells us that 2 to the third power is 8. Now, base 2 is very important in computer science, but you're not going to run into it too often in many other disciplines. Base 10 is very heavily used in science, scientific applications, but it's the natural log that we really will use the most often in areas like mining, economics, let's say, because as we saw last time, we can use them to help us calculate interest rates, especially when interest rates are continuously compounded. So the natural log, which is log to base e, is the one that we're going to see most often. All right, now, in general, the log of base b of x is equivalent to saying b to the y power equals x. And remember, b is the base. So the base can be anything, but like I said, there's only a handful that you might run into in practice. Base 2, for example, base 10, and base e. The others, it's kind of hard to visualize an application that needs log to base 6, for example, or log base 7. But in principle, we can define any base we like. Now, oh, by the way, let's use our old friend Symbolab real fast to look at a graph of log x. Let's try log base 10, I guess. Or actually, let's just do the natural log. And so I'll ask it for a graph. And we're going to see something interesting. If you notice, the vertical axis is an asymptote to the function. The function never quite reaches 0. So in other words, as far as the domain and the range are concerned, you'll see here that the domain is everything from 0 up to positive infinity, but not including the 0. Okay, in other words, from here on, all the positive values are in the domain of log x. And that, by the way, doesn't depend on the base. It says here log base b to indicate that this is true for any base. But the example I'm showing you here is natural log, but this is always true. It doesn't matter what the base is. the range will always, sorry, the domain will always be 0 up to infinity, not including 0. On the other hand, the range, you can see that all the y values are covered. There's nothing here to prevent us from having a range of any real number. So the range is all the real numbers. Okay, now sometimes the base 10 logarithm is called a common logarithm. Like I said, you ran into this probably in chemistry class in high school. You see it used for certain measurements, like the pH measurement you saw in high school chemistry is based on log 10, as is the Richter scale for earthquakes. So, if you went to the internet, you could find a bunch of applications that do in fact use the log to base 10. And so, for example, here, the log to base 10 of 10,000 would be 4, because the 10 to the 4th power is 10,000. And then finally, the one we're going to see the most often, log base e, is written as ln, or natural log. And that kind of gives you a sense of, there must be a reason for calling it the natural log. It proves to be extremely useful in practical applications. You don't get to be the natural log unless this is the most important one. Okay, now a few important details. The log, some special cases, no matter what log we're looking at, the log of 1 is 0. And that's because any value b raised to the 0 power is 1. The log of base b itself is just 1. So the log to base 2 of 2, for example, is 1. And that's because b to the 1st power is just b. Now, here's where it gets interesting. And sometimes these properties I'm about to show you can be used to simplify a very frightening looking equation and turn it into something much simpler. The log to base b of b to the x is x. Okay, so let me just throw in a specific example here. The log of e, let's say, to the x is just x. Because remember, ln is log base b. So here the implied base is e. So therefore, we end up with x. And then here's another one. B to the log b x is equal to x, which is equivalent. Let's say that you have e to the log x equals x. It's true for, and again, it's true for all bases, but these are the ones you're most likely to run into. Okay. Now, algebraically, there are several rules that we can apply to logarithms. You might recall, if you've seen this before, that the log of a product is equal to the sum of the individual logs. Okay, so for example, the log of xy could be written as log x plus log y. And again, sometimes this is helpful, sometimes it's not. It can often be used to help us simplify problems. Or equivalently, you can have something like this. All right. So if that, here's another one. Log base 10 of 100 is 2. But what this is showing us is that if there's some reason for doing this, we could have rewritten this as log base 10 of 10 plus 10, because obviously 10 times 10 is 100. And that would also give us 1 plus 1 or 2. Now, why would you want to do this? Again, it depends on a particular problem you have, but it might make it simpler to solve. So in other words, the reason for knowing these properties is because you may end up being able to simplify problems and therefore solve them more easily. Or here's an interesting one. You're multiplying 3 numbers together. So this is equivalent to having a sum of 3 individual logs. Log 3 of 2 plus log 3 of x plus log 3 of y. Now, if you ended up with something like this, more likely you'll turn this into this, just to simplify it a little. Because as you know in math, we always like to simplify our results whenever possible. So you may not want to go, if you already have log 3 of 2xy, you may not want to convert it into the second expression, but you may want to go the opposite direction. Now, because the product of 2 logs equals a sum, it stands to reason that a quotient would result in a difference. And that's exactly right. So the quotient rule says the log of x over y equals log x minus log y. So let's say or let's do a more complicated one. Okay, so the bottom line is you're turning the log of a ratio into a difference of two logs. Okay. All right. Oh, look at this one. Oh, by the way, I just want to make it very clear. When you're done with this, you notice how all the terms have to have the same base. Otherwise, this doesn't work. Okay, it's understood. Like if you have this result and you want to turn it back into a ratio, it can only work if the two logs have the same base. Okay, so just be aware of that. These rules are only going to work when we have the same bases. Now, this is the one that I find to be particularly useful, the power rule. You'd be surprised how often this will show up. The log base b of x to the n power is the same as n times log base b of x. So if you had the log of e squared, this is the same thing as 2 log e. Okay, so here you have log base 2 of x cubed is the same thing as 3 log base 2 of x. Okay, so again, you know, when you use this, it depends on the problem you're working with. Okay, now here, what I've done is I've shown you why this works. So remember, log x squared is just x times x. So if we rewrite this as log x squared of is the same as log x times x, I can use this sorry. Let's go back here real fast. I can use the product rule in a very interesting way. I can take this expression and rewrite it as log b of x plus log b of x, which is obviously 2 log base b of x. And so basically what we're seeing here is that this is the reason why this rule works. Okay, because we're just using the product rule multiple times. Now, this also works with fractional exponents. It's not just for integers. For example, the log to base 10 of radical x, because radical x, of course, is x to the 1/2 power. I can rewrite this as log base 10 of x to the 1/2, or simply 1/2 log 10 of x. All right. Oh, here's an interesting one. This one requires us to use 2 rules. And you can certainly do that. You're not just restricted to using 1 rule at a time. Whatever goes. I mean, again, as long as the base is the same for all the logs, you can feel free to use all of these properties. Here's a good one. So you've got a quotient and a product. So in the numerator, we have x to the 4th times y, so we can rewrite the numerator. And then we subtract the denominator. And this is my final result. Now, of course, like I said, I mean, you wouldn't, if you have this, you wouldn't normally convert it into this because you're just kind of making a mess. But what you might do is take this and turn it into this. So the important thing is that you recognize that they mean the same thing. All right. So we've got a couple more interesting ones. With fractions, I mean, hold on. All right, so using the same logic, the log 10 of radical x is 1/2 log 10 of x. Now here's an interesting one. Radicals, the cube root of x squared can be written as x to the 2/3 power. And once you recognize that, then you can see that this is simply equal to 2/3 log x. All right, let's look at a few more. Now for log x, now this, you see here, we're working it backwards. We're taking the exponent rule, I'm sorry, the power rule, and we are taking 4 log x and rewriting it as log to x to the 4th, which we are certainly allowed to do. In this case, what we're doing is we're taking this and turning it into log base 3 of 2 to the 5th. And since we can figure out what that is, up here we have x to the 4th, we can't really do anything with it. But since we know what 2 to the 5th is, we can rewrite this as log base 3 of 32. And then this one, 2 log 10, base 10 of 100 is equal to log base 10 of 100 squared, which is 10,000. And now this one can be simplified into 4 because 10 to the 4th is 10,000. Now, here's an interesting result. What will sometimes happen is that you may have a base for your log, which is not convenient. And you may want to figure out, well, can I convert this into another base? Is there a rule that enables me to switch from one base to the next? And it turns out that there is such a rule. So let me just show it to you real fast. And the reason why this is so important, well, we'll see in a second, one important way this can help you out. So if I have log base b of x, what I can do is I can rewrite it as the ratio of 2 logs with any base that I choose of x over b. As long as these are the same, I can pick any base I like. Okay. How interesting. So I can feel free to convert one logarithmic base into another using this formula, which I think you'll get a lot of use out of. And so here's another quickie. What if I had this? It turns out I can randomly pick log base 2. And it's a log base 2 of 100 over the log base 10, 2 of 10. Okay, now here's one of the more interesting uses of this. What if I had something like this? Now, you notice how here I arbitrarily chose a base of 2. What if I'd chosen base e instead of 2? Then I'd have the natural log of 100 over 10. Now, why is this so important? Because if you look at your whatever calculator you have, even if it's a very powerful one, there's a very real chance that it has a natural log button, but not any other log buttons on it. In other words, it may not have a log 10 button. It may not have a log 3 button. So what that means then is that on a calculator like that, if you have a base other than e, it doesn't really matter because you can convert it into a ratio of 2 natural logs, and then you can use that on your calculator. Okay, so if you look at your calculator really carefully, you may see, I don't know which calculator you have, but it does not have any keys for logs other than the natural log. And if that's the case, then this formula could potentially come in very, very helpful. So remember this, it's very powerful, okay? Just be aware that this is here in case you need it. All right, now we're going to solve some equations. And you'll start to see how powerful these logarithmic equations really are. So let's just say we have a very scary looking equation. For example, 2 to the x minus 1 power equals 2 to the 2x minus 4 power. What are we supposed to do with that? Well, what you're actually going to do is this. And by the way, let me just go remind you which property this is taken from. Here we go. This is where the logic comes from. Yes, it looks scary, but it's going to be very, very helpful. Okay, I'll leave it up in the title. It doesn't really matter because here's what we're doing. If you've got this expression, 2 to the x minus 1 power equals 2 to the 2x minus 4, if you apply the log base 2 to both sides, which we're allowed to do, any equation can be solved by applying the same technique to both sides. Based on this property up here, this reduces to now it's easy to solve for x. So this is going to come in very helpful. When we're trying to solve these, remember, these are exponential equations because the x is in the exponent. Now, of course, they have to have the same base. Otherwise, this isn't going to work. But if they do, you can just essentially get rid of the bases and just rewrite this as x minus 1 equals 2x minus 4. But the reason why you're allowed to do this is because you're essentially just taking the log base 2 of both sides, which we know is permissible because you're not changing anything as long as you apply the same function to both sides. And of course, you can easily solve for x. Now, this wonderful ability to do this is often known as the one-to-one property of exponential functions. And so what it's basically saying is that based on the logic we just saw, as long as the base is not 1, b to the s power equals b to the t power, if and only if, or only if s equals t. So that means we can just ditch the b's and rewrite this as s equals t and then solve. Wow, what a powerful property that is. And of course, this just means that x equals 3. And you can certainly double check that. Let's just plug in that 3 and you can see that, yes, both sides are equal to 4. Now, this next one you'll find interesting because at first glance, it doesn't look like we can use this one-to-one property. But if we use our cleverness, it turns out that we can. All right, watch this. So you look at it, oh, what is this? 256 equals 4 to the x minus 5 power. Oh, but wait a minute. 256 is 2 to the 8th, isn't it? Yes, it is. So how does that help us? Oh, but wait a minute. Here's the interesting part. 4, of course, is 2 squared. So you actually have 2 squared raised to the x minus 5 power. And that turns out to be the same thing as 2 to the 2 times x minus 5 power, or 2 to the 2x minus 10 power. This is why, okay? So in other words, if you had something a little simpler, like 3 squared to the 3rd power, this is the same thing as 3 to the 2 times 3 power, or 3 to the 6th. So now, all of a sudden, I've got 2 to the 8th power equals 2 to the 2x minus 10 power. And now I can apply that one-to-one property. And all of a sudden, 8 equals 2x minus 10. And now it's a simple matter to solve for x. It turns out to be 9. Well, that was pretty interesting. Oh, yeah. Now, there's other things you could have done too. But just by rewriting them with the correct base, or the same base, I should say, this way you can apply that one-to-one property and make things a lot simpler for yourself. Now, here's another set of strategies we can use. An exponential equation may be solved by rearranging it algebraically, well, as we just said, so that all the terms have the same base. What does that mean? Let's try it. Now this one is pretty straight ahead because you've got 3 equals 4 to the 3 to the 4x minus 7. Here, this is 1. And remember, this is the quotient rule right here. So this is actually 3 to the 2x minus 3 to the first. But when you have the same base like this, this is very simply 3 to the 2x minus 1 power. So by rewriting it like this, you can now directly set with the one-to-one property, 4x minus 7 equals 2x minus 1, and then you can go ahead and solve for x. And that turns out to be 3. Nice. You see how nice it is when you make your life so much simpler by using these amazing properties? Yes. In fact, a lot of times the motivation for using these properties is just to simplify everything. Now, here's a good case. Here we have what appears to be an exponential equation, but unfortunately, you'll see that they don't have the same base. Oh no. So now what are we supposed to do? It would be nice if they did. And furthermore, it's not the case that we can rewrite these like we did back here. This one, even though the bases were not the same, we were able to rewrite these to come up with the same base. So that was our strategy for that one. This one is different. We don't have that ability. There's really nothing we can do to give them a common base. So here's what we're going to do instead. We're going to take the natural log of both sides and use the properties we saw before. So for example, here, log of 5 to the x plus 2 power becomes x plus 2 log 5. This one is now x log 4. So I'm doing a little algebra here. I'm trying to get all the x's on one side and the log, the constants on the other side. Okay. So we're not there yet, but on the left-hand side, if you notice at the bottom there, we do have a common factor of x, which is very helpful. Okay. The right-hand side, we just have a constant. Negative 2 log 5 is a constant. All right, then. Let's see what comes next. So I've got x log 5 over 4 equals minus 2 log 5. So there's nothing to stop me now. Log 5 over 4 is a constant. And all I have to do is divide both sides by that to come up with x. Now, the final result is not going to be pretty at all, not even close, not something that can be simplified, but at least we have an answer. So what you can do now is plug that in. If you need the actual value, you can plug that into your calculator, or you can plug it into Excel or some software, or like Symbolab could do it. And you have your actual constant result. But what we were able to do was take a case without the same base. And by taking the same log of both sides, and it didn't have to be natural log, it could have just as easily been log 10 or any of the others. We were able to rewrite it and come up with an expression in terms of those logs. In other words, if it had been log 10, you would have had log base 10 of 5, log base 10 of 5 over 4. The interesting thing is it doesn't really matter which base we use, you'll get the same result. All right, and then sometimes, you know what, we can solve equations, logarithmic equations, just by looking for the properties. For example, let's see, what can we do with this one? Now you see, they both have the same base. And so this is the case where we have the log b of x, log b of y. So that's what's happening here. And then that can be rewritten as log base 2 of 6x minus 10 equals 3. Now remember, log 2 of, let's say, 8 is 3 because 2 to the third is 8. So what that implies here is that 2 to the third equals 6x minus 10. And now you're all set, because you can just write this as 8 equals 6x minus 10. And eventually you'll discover that x equals 3. So instead of having to stop here and say, well, I don't know what to do next. I mean, imagine trying to rearrange this thing. I don't think that would work out too well, but then all of a sudden, it turns out it's very simply equal to 3, because we use the properties of logarithms themselves. The actual definition of a log enabled us to rewrite it this way. All right, so that one was pretty tricky. All right, let's do another one. This one involves natural logs. So you get something like this. 2 log x plus 3 equals 7, 2 log x equals 4, log x equals 2. All right, well, now what? Now here's the clever part. And I'm allowed to do this. Like if I had something like this, if I had x equals 2, I'm allowed to rewrite that as 2 to the x equals 2 squared. And it means the same thing. So now remember, from one of our properties was that b raised to the log b of x equals x. So e to the log x, as we saw earlier, equals x. And so this tells me that x equals e squared, whatever that is, and I'm done. So you know what? These properties give us the ability to really solve a lot of extremely messy equations, as long as we remember the actual properties of exponential functions and logarithmic functions. Here's a good one. It's very similar. 2 log 6x equals 7. We divide both sides by 2. Same thing. I'm going to just take this and rewrite it as e to the log 6x. Remember, e to the log x equals x. That means that e to the log 6x is 6x. So 6x equals e to the 7 halves. And I end up very simply with, right, whatever that number is. All right, one more example. Now, let's just quickly review one thing we started out with. The one-to-one property of exponential functions basically said, in fact, I'm going to copy this into the next slide so you can see it. You can see these side by side. It turns out there's a similar, an equivalent property for logarithmic functions. So b to the s equals b to the t if s equals t, which implies that the same thing can be said of logs, okay? So if I have log base b of s equals log base b of t, that can only happen if s equals t. So it's the same idea. The only thing is I just realized they're caps, but that doesn't really matter. But still, we can use that same idea to solve for these problems. So for example, I have log 2 of 3x minus 2 minus log 2 of 2 equals log 2 of x plus 4. I can use the properties of logs to rearrange these. Okay, since these are, this is a difference, I can turn it into a quotient. But if you notice, both sides have log base 2. So you know what I can do now? I can just rewrite this very simply as 3x minus 2 over 2 is x plus 4, because they have the same base. And now it's just algebra. Simple algebra. So let's jump ahead and look at that. And there it is. Wow, that was interesting. Man, these log functions are pretty interesting. And so we'll see them fairly regularly throughout the rest of the course. All right, so now we're going to completely switch mental gears. And we're going to be looking at trig functions. Now, trig functions are something you've all been exposed to, but you've probably not seen them for quite a while. So we're going to take a look at these. We'll need them throughout the course. And of course, you know, the ones you end up using all the time in practice will depend on what discipline you're studying. Like if you're studying engineering, you'll need these all the time. But in other disciplines like finance and economics, you never use trigonometry. They don't seem to lend themselves well to financial applications because I guess it's just because they're periodic functions and you don't see that a lot in business applications. But anyway, here's the six basic trig functions that you know and love: the sine, the cosine, the tangent, the cotangent, the secant, and the cosecant. Now, you might remember that these are related to each other. These are not actually 6 totally different functions. For example, the cotangent is 1 over the tangent. Okay. The secant is actually nothing but 1 over the cosine. And the cosecant, which is abbreviated CSC, is 1 over the sine. So these are actually not separate functions. And in fact, they're just functions of these 3. Okay. All right. Now, just as a quick reminder, you've done this the first time you were ever introduced to this stuff. I am sure that they tried to give you some kind of mnemonic device to help you remember them. Like this one, Sakatoa. You might remember that from whatever grade you were in. What is this all about? Well, the sine is the opposite over the hypotenuse. Remember, these are defined in terms of a triangle. So this is the angle you're interested in. This is the adjacent side. This is the opposite, and this is the hypotenuse. So the sine is the opposite over the hypotenuse. I'll just abbreviate that. The cosine is the adjacent over the hypotenuse. And then the tangent is the opposite over the adjacent. Okay, so I just want to remind you, in case you've forgotten, this is that mnemonic device you were taught somewhere along the way, and it was designed to help you remember the first 3, and then you recall that you can get the rest of them. For example, the cotangent, since it's 1 over the tangent, that implies that it's the adjacent over the opposite. The secant is 1 over the cosine, which means that it must be the hypotenuse over the adjacent. And then finally, the cosecant is 1 over the sine, which implies that it is the hypotenuse over the opposite. And, you know, we'll see this again. Don't worry. I just want to remind you how this works. And there's definitely some slides further on that review all of this good stuff. Just to refresh your memories. So we're going to take a step back and define more formally some of this. For example, the concept of the angle. An angle is the relationship between two rays that have a common endpoint. Remember, a ray, a straight line goes on forever in both directions, but a ray has a specific starting point. Okay, and so it goes on forever in one direction, but it starts at a specific point, whereas a line goes to positive and negative infinity in both directions. So an angle is the relationship between two rays that have a common starting point. For example, let's take a look at this. Here we go. And we often see that angle described with the Greek letter theta. Essentially, it represents the spread between the two rays. Now, there's some terms you might have forgotten here. For any angle, we're going to have what's called the initial side, or think of it as the starting point, the terminal side, which is where we end up, and the vertex is right here where the two touch, okay? And then this would be the angle. So this is all being done, of course, within the standard XY coordinate system. And you'll recall that the theta is measured in degrees, going from this axis to this axis is 90 degrees. Going all the way here brings us to 180. Then this is 270. And then this is 360. So why is this all based on 60s? You have the ancient Babylonians to thank for that. So yes, so a circle has, as you recall, 360 degrees. The four quadrants that we know from the XY coordinate system each contains 90 degrees. And if you notice, when we move around the circle, we're going in a counterclockwise direction. That I don't understand, but that's how it turned out. You would think it would be the other way around, but no, it goes in a counterclockwise direction. And so therefore, a single degree could be defined as 1/360th of the distance around the circle. Okay, in other words, the angle is thought of as the amount of rotation between the initial side and the terminal side, or how far do you have to go from the initial side to the terminal side. A degree is 1/360th of the entire circle. Now, there's some terminology that we want to get out of the way here. For example, standard position simply means that the vertex of our angle is the origin, in other words, 0, 0. This is how we usually think of angles, starting from the cross where the XY coordinates cross. And you notice we do move in a counterclockwise direction. So interestingly enough, if we go from in this direction, these are all said to be positive angles. If we go the other direction, the angles are actually defined to be negative. Well, that seems kind of strange because they're going the opposite direction. We'll see in a few minutes how that works. But those are defined to be negative angles. I just realized I drew this incorrectly. Whoops, hold on one second. I fix it. Going in that direction. In other words, going in a clockwise direction means you actually end up with negative angles. Okay, so like here's a 90-degree angle. We're going counterclockwise through one full quadrant. That's 90 degrees. Now, here's where it gets interesting. What happens if we go the opposite direction? So basically what you're seeing here is that we went 90 degrees to the fourth quadrant. And then another 45 into the third quadrant, which adds up to 135 degrees. But since we went in a clockwise direction, we define this as not 135 degrees, but negative 135 degrees. Okay, it's not the same. Positive 135 would be here. All right, well, I didn't draw that very well. Because it's 90 degrees plus another 45, and we're going in a counterclockwise direction from the first to the second quadrant. So they're not the same angle. Okay. So just remember, if you're going in a clockwise direction, the angle is defined to be negative. If you're going in a clockwise, counterclockwise direction, it is said to be positive. All right, so here we have the four basic angles. 0 means you haven't moved at all. 90 went through the entire first quadrant. 180 is this into the second. Then 230, and then for some reason this diagram doesn't have 360. Well, 360 is really the same as 0, because you're still right back at the same starting point. Okay, so just be aware 360 and 0 mean the same thing. Is it all coming back? I hope. All right. Anyway, so this is more terminology. This isn't really that important, but those standard angles that we just looked at, 0, 90, 180, 270, and 360 are called quadrantal angles. I don't think that's very important, but there it is. Okay, now the next thing we're going to do is something that I found to be a pain when I first learned about this. We're going to convert angles into what are called radians. Well, okay, here's all you have to remember. 2 pi radians is the same thing as 360 degrees. Now, who knows where this came from? Somebody invented this idea. They must have thought it would be simpler. I don't know. I think the degrees are just fine the way they are, but this implies that 1 radian is equal to approximately 57.3 degrees. Just remember this relationship, or you can even think of it as simply pi radians is 180 degrees, or half the circle. So 2 pi radians is the full circle. And here's a little chart to help you remember this. So there you go. And so in each case, what you're doing is starting with the definition, pi radians is 180. That implies that pi over 2 must be 90, pi over 4 is 45, et cetera, et cetera. All right. And there, you can then use this to calculate any of the other ones. For example, 3/4 pi must be 135 degrees. Again, using your starting point, if pi radians is 180, 3/4 of that is 135. Oops, okay. All right, now, here we're going to show you the relationship between positive and negative angles. So it turns out sometimes, negative angles can be a pain. My guess is that if you try to put negative angles into a calculator, it's not going to work correctly. So here's what we have to think about. we're going to define what are called coterminal angles. Now remember what terminal means. We start with any angle with the initial side, and we end up with the terminal side. The terminal side for any two angles that have the same terminal side, we call them coterminal. Okay, now here's an example of what I mean by that. So if we start at the origin and we go counterclockwise, 50 degrees into the second quadrant, there's 90 plus another 50. We end up here. If we go the other direction, clockwise, we've got 90, 90, and here we're going 40 degrees into the second quadrant. These three add up to 220. But remember, we're going in the clockwise direction, so we call it negative. So what they're saying here is that negative 220 and positive 140 are coterminal, or just, we don't really need the dash, coterminal, because they bring us to the same location, starting from the origin. In other words, they're the same thing. So if I needed to, I don't know, I'm building a birdhouse, let's say, and I want the water to be at a 140 degree angle or something like that. 140 and negative 220 will give me the same result. So we call them coterminal. And why is that important? Because if you do end up with negative angles, it's easy to convert them into an equivalent positive value. So as long as you're aware that they mean the same thing. Now we have the concept of the reference angle. By the way, just in case you've forgotten, an acute angle is one that is less than 90 degrees. Let's see. So an angle's reference angle is the smallest acute angle that can be formed from the terminal side and the horizontal axis. What does that mean? All right, well, let's look at this chart. And we'll see that the calculations are different in each quadrant. So for example, let's say I'm thinking about I don't have a lot of good examples here already. Let's say that the angle I have in mind is 400. So that means I've gone around all the way through the circle and then again another 40 degrees. That tells me that the reference angle of 400 is 40. And in other words, what you're basically doing, you're given that the number of degrees can be very large, depending on how many times we went around the circle. It might be easier to convert it into the so-called reference angle so that we can compare them directly to each other. And of course, this also implies that, let's say, 760 has a reference angle of 40 as well, because it means we went around the circle twice and then another 40 degrees. So these are the same angles with respect to the origin. The one that we'll try to use so that we can compare them directly to each other on an equal footing is the reference angle. So when we have these enormous angles, it might be simpler and easier to simply use the reference angle rather than the actual angle itself. Okay, and we could do something similar for all four quadrants, but the logic is that we want to convert it when we have something that's really large. We want to be able to convert it into something equivalent. We can do the same thing with radians, except that instead of thinking in terms of 180, we think in terms of radians. For example, remember the entire circle means 2 pi radians. So 3 pi would mean going around the circle once, okay, and then moving 100 pi radians into the horizontal axis. So 3 pi radians is the same thing as pi radians, because it just simply means we end up here. All right. Now, by the way, just when we get further into the course, we're not really going to be spending a whole lot of time with radians, and we're not going to spend a whole lot of time with a lot of these definitions. But what's going to end up happening is we're going to use these basic trig functions, and we're going to need to apply different properties to them. So while this is good background, we don't really need to become experts in trigonometry. We just need to remind ourselves how these functions behave. So a lot of these terms are not going to prove to be all that important. Not that we shouldn't know them, but that's not going to be the focus. All right, well, anyway, with that being said, we're going to introduce a very important idea that'll actually help us figure out some of these sines and cosines and tangents. We're going to introduce something called the unit circle, which means that it's centered at the origin. In other words, the point 0, 0, and the radius is equal to 1. Okay, now remember the radius cuts the circle in half. The diameter would go all the way down here. Okay, but the radius is just 1, and that's chosen for convenience. We can derive a lot of results with this unit circle. So, quick reminder, let's say we have the triangle 1, the sides are 1, radical 3, and 2. Now remember from the Pythagorean theorem, a squared plus b squared equals c squared. Is that true here? Yes. 1 squared plus radical 3 squared equals 2 squared, right? Yes. And so whatever that angle is, we can figure out the sine, the cosine, the tangent, and all the rest by using the definitions. So, for example, the sine where sine is opposite over hypotenuse, which means 1 over 2. The cosine and by the way, this, you might remember, this is 30, this is 60, and this is 90. Triangle has to have 180 degrees. So the cosine is adjacent over hypotenuse, which is radical 3 over 1, which is radical 3. Radical 3 over 2. This is the hypotenuse. And then the tangent, opposite over adjacent. 1 over radical 3, which is equivalent to radical 3 over 3. Yeah. And oh, by the way, just as a quick reminder, when we have something like this, 1 over radical 3, in math, we try to avoid having an irrational number in the denominator. So what you can do is apply a technique called rationalizing the denominator. What does that mean? You're going to take whatever's in the denominator and multiply the ratio by that over itself to avoid changing the value. So there you go. So these are the same thing, except that the second one does not have that irrational number in the denominator. It's just it's kind of like any math test you ever had. Remember, if you had a final result of 8/6, you would just automatically convert it to 4/3. It's a similar idea. There's nothing wrong with having a radical in the denominator. It's something that mathematicians try to avoid. And so normally you just automatically convert that to radical 3 over 3. Well, all right then. So watch what you can do now with all of this. Look at this diagram. Now it looks terribly complicated, but what it's going to do is show us how to calculate sines and cosines with this unit circle. So let's say we have t. Now I did say before, 1 is the the radius. And so we form a right triangle, which means that this is a 90-degree angle. And from the perspective of t, this is the opposite, this is the adjacent, this is the hypotenuse. So the sine of t the opposite of t, well, let's look at it. This vertical line. Now keep in mind, this is a unit circle. The radius is 1. The only way that can happen is if this is the 1, 1. Actually, no, sorry, that's not right. This is 1, my fault. No, let me take that back. No, that's not what it says at all. Let me take that back really quickly. Because here's what's going to happen. The height of this opposite is y. Okay, so the opposite is y. Okay. So the sine, and by the way, remember the hypotenuse is 1. Whatever y is, so that y is actually the sine of t. And then since the cosine, the adjacent is right here. Now, that is equal to x. So you're going to have cosine t is adjacent over 1, which is x. So because we have a radius of 1, this xy pair is cosine t, sine t. So now, of course, we don't know what they are because we don't know what angle T is. But let's just say that angle T is 45 degrees. We know what the hypotenuse is, but we don't know the sine and the cosine because we don't know what T is. But let's just say we have, this is our example. 45 degrees is this T, and which means this also is 45 degrees up here, because remember, they have to add up to 180. And so that means that these two are equal to each other. So now we have a squared plus b squared equals c squared. Okay. Now, since x equals y, x squared plus x squared equals 1 squared. Okay, so what does this even mean? And remember, x is the cosine of this t. And so since x equals y in this case, so in other words, they're both the same, 2 over radical 2. Sorry, what did I do here? It's 2 over radical. Sorry, radical 2 over 2, my fault. So in other words, by using this diagram, what we just did was saying, listen, if you don't have a calculator, we just proved that the sine of 45 is radical 2 over 2, and the cosine of 45 is radical 2 over 2. By using the unit circle and the definitions of a right triangle and the definitions of sine and cosine. So you can, in principle, go through this entire circle and do the exact same thing for 30 and 60 and 90 and all the rest. And the slides go through all of these in great detail. Here's a little summary of some of the key highlights. We're not going to do that here. We don't really, it's not important enough to spend a lot of time with. It's good to review the trig functions, but we don't need to get too deeply involved. But I just wanted to show that that is one way you can demonstrate how to calculate the sines and cosines from those different triangles that we can use. So here's some of the more important ones. And so just a quick, one more thing here. For sines and cosines, let's just go to Symbolab for a second and do some graphs. What we want to do is quickly review the domains and ranges. So you'll recall that these functions, yeah, it's like it just goes through a cycle over and over and over again. And you can see that here, any x value is possible. The y values are bounded between -1 and +1. So therefore, we say that the domain for the sine is -infinity to +infinity. The range is -1 and 1. And as it turns out, if you look at a graph of the cosine, the same thing is true. Okay, let me just quickly prove it. Yeah, same thing. I mean, the cycle is different, but you can see that the same thing is happening. All x's are possible, and the y's have to be between negative and positive 1. Some of these have, like the tangent has some discontinuities in it. There are a couple of places where it's undefined. Let's just quickly look at that one. Ooh, there's several places. Yeah, there you can see it has several vertical asymptotes. So, but anyway, but the sine and the cosine are very well behaved. So what we need to do now is just take a brief review of how these other functions are related to the sine and cosine. And then we can kind of wrap this up a bit, because I think we really want to get rolling on the limits. And so while this is kind of important and kind of interesting, it's not, like I said, our primary focus. So we'll run through this part fairly quickly, and when we get back from the break, and then we will start limits. Okay. So I hope this is refreshing your memories. It, it's coming back. You're probably remembering all this good stuff, but it's probably been a while. So, all right. So we'll have our break, and when we get back in about 10 or 15 minutes, we'll go through and look at these other functions: the tangent, the cotangent, the secant, and the cosecant. Look at their properties, and we'll also see some other equivalent versions of the Pythagorean theorem as well. All right, so let's knock it off for a bit, and we'll pick it up when we left off. Stressed out. Time to refresh. All right, so now we can take a closer look at these other trig functions. Of course, we tend to use the sine and the cosine most often, but we need to understand these as well. So for example, the tangent, cotangent, secant, and cosecant. So we already know the tangent is the opposite of the adjacent. And that implies, as it turns out, if you do the algebra, you'll see that this is equivalent to the sine over the cosine. And of course, that means that on this unit circle that we were just describing earlier, that implies that the tangent is the ratio of y over x. Okay, so whatever this angle is, call it t, the tangent then would be calculated as y over x on the unit circle. Then, of course, this implies that the cotangent is just the inverse of the tangent, which means that it's 1 over the tangent, adjacent over hypotenuse, or you can think of it as cosine over sine, so that on the unit circle, that means that it must be x over y. All right, now the secant is the inverse of the cosine. All right, so remember that the on the unit circle, the x-coordinate is the cosine, the y-coordinate is the sine. And so if the secant is the inverse of the cosine, that just means that it's 1 over x. All right, and then of course, finally, the cosecant is the inverse of the sine. So let's just put this in here one more time. And that implies that this is just 1 over y. Okay, now here's just a quick review from the last section. We've earlier defined the notion of even and odd functions. Okay, so for example, an even function would be something like this. F of x equals x squared. Because f of negative x would also simply be x squared. Down here with the odd functions, you could have something like this. Negative f of negative x would be x cubed, because f of negative x is negative x cubed. So in other words, what you're really trying to capture, the x squared even basically means that the function will not appear, in this case, in the third or the fourth quadrants. In this case, it will. So we could do something similar with the trig functions. it turns out that the cosine and the secant are even. And we can prove this just by taking out the calculator and trying some of these, but or else we could show the graphs. And then the other four are odd, as it turns out. Okay. All right, so let's see. We want to now trig identities. Sometimes we can take these definitions and turn them and simplify our trigonometric expressions. And of course, that's often a major goal of using these definitions, is to come up with simpler equations to solve. And so here's some simple examples of this. Just a quick reminder, the tangent is equal to sine over cosine. Secant is the inverse of the cosine. Cosecant is the inverse of the sine. Cotangent is 1 over the tangent, or cosine over sine. So with those in mind, we can take something like this. Suppose you were confronted with this question, secant t over tan t. If you were to write out these definitions, you'd notice something interesting, that surprisingly enough, this is also equal to the cosecant of t. Okay, how is this possible? Well, the secant, remember, is the inverse of the cosine. The tangent is the sine of the cosine. These cancel out. And you've got 1 over the sine of t, but of course we know that that's equivalent to the cosecant. So, you might, depending on how you look at it, like especially if you're trying to calculate derivatives, often the simpler the expression can be, the better off you'll be. It'll be easier for you to get your results having cosecant by itself rather than secant over tangent. All right, so now we're going to just take a quick look at a few equivalent versions of the Pythagorean identity. And of course, what's happening is we're rewriting these terms based on these definitions to come up with some equivalent versions of the Pythagorean identity or Pythagorean equation. So we know oh, by the way, you know what I forgot to put in here? Well, no, this is fine. I mean, a squared plus b squared equals c squared is, of course, the main Pythagorean equation, but that implies that this is true. No matter what t is, the sum of the squared cosine and the squared sine is equal to 1. But we can use the definitions of these trig functions to rewrite this in terms of 2 other equivalent versions. And for some equations that might, or some problems that might prove to be very useful. So we're going to start by seeing what would happen if we were to divide both sides of this expression by cosine squared. All right, so if we do that, the first term, of course, turns into 1. Now, what about this one? So it's the same thing as the definition of tan t, except that this is the square. Now, one thing I do want to point out is with this notation, by writing it like this is the same thing as this. Okay, so I think that would make it a little easier to see this. Okay, in other words, yeah, I don't know why they choose to write it like this, sine with a little square, but for the t, it means the same thing as sine of t squared. It's the same thing. So that reduces the squared tangent of t. And of course, that also means that since the secant is the inverse of the cosine, logically, the secant squared must be the equivalent of 1 over cosine squared of t. So that's where this is coming from. Ah, there you go. And of course, if you rewrite this algebraically, that tells us that secant squared minus tangent squared of t just equals 1. All right, there is one more. If we divide both sides now by the sine squared of t, let's see what that turns into. And of course, we're allowed to do that because it doesn't change anything. The first one, now remember the cotangent is equivalent, is 1 over the tangent. So therefore, this must be the cotangent squared. This is just 1. And once again, the cosecant and the sine are inverses of each other, so we end up with this. All right, now I'll tell you what, there's more here, but I think that is probably enough for now. We can come back, revisit this if we need to when we go to start doing derivatives. I really would like to get started on the limits. I'm looking ahead here and I'm seeing there's a lot of, this is pretty intense. We don't really need this much coverage of trig functions right now. We may have to come back to this and revisit it, but I think it would be better as far as time is concerned, for us to jump ahead now and actually start looking at chapter 2, which is our introduction to limits. All right, so let me go get that open. Here it is, 2a, limits. So we're going to introduce this concept of the limit, which in turn we'll use that later on to introduce the concept of the derivative in chapter 3. And of course, a large chunk of the class will be based on the notion of the derivative. Okay, so we're going to start out with something that might be a review, and that would be the notion of the secant line. So remember, here's a function. This would be a tangent line because it touches the function exactly once. So that's a tangent line. A secant line cuts through the function twice. So we're going to use the secant, the notion of the secant, to help us understand what a limit is. Okay. So here I borrowed some graphs from the book because they're so much better than anything I could produce. Let's start with this case. This could be any function. And you've got 2 points, a f of a, x f of x, and the slope of that line, that secant line, is the rise of the run, delta y, over delta x, where we're assuming that this is the first point, second point. So in other words, this is the same thing as y2 minus y1 over x2 minus x1. Now, we don't, of course, know what these values are. So what we can see, though, is that this is the slope. Now, here's what we're going to try to do. What if I really am not interested in the secant line, but I'm really interested in a tangent line? Now, we did go over this in 1B or 1A, this notion of rate of change. Let's go get those notes back for a second. Just as a quick review. Oh, I almost forgot. It doesn't seem to work if you're in that mode. There we go. There we go. This is how we defined in part 1A as the rate of change between 2 points. Okay, so we did this for gas prices over a period of 10 years, and we did the same thing for stock prices over a period of 5 years. But this is the definition: rate of change between 2 points. So keep this in mind. What we would like to be able to do, though, is define the rate of change at a single point on this curve. Okay, so what we're going to do, this will be our strategy. We're going to choose 2 points now that are closer to each other. So the blue line is the new point. The red one is fine, but let's try this point now. So we'll calculate the slope of the tangent line again, and then we'll do this. And what we'll keep doing is we'll keep choosing X and A to ensure they're getting closer and closer to each other. So if we had another one, let's say there's a green line that's getting even closer. So what we're trying to do is essentially minimize or eliminate the difference between the X and the A. And once we have reached the point where X and A coincide with each other, what we end up with is the tangent line right here. This is the tangent line to the entire function. So in other words, the slope of the secant line is converging to the slope of the tangent line at point A, f of A. So it's kind of hard to see it, but I mean, each time we chose a new line, let's call this line 1, line 2, and line 3. So we're going to keep choosing lines where the X's are getting closer and closer and closer to this A. And eventually we'll reach a point where we have now our secant line equals the tangent line when X equals A. Okay. So what does this have to do with limits? Well, you can think of this tangent line as the limiting case of all these different secant lines. In other words, we keep drawing more and more secant lines. They get closer and closer to the tangent line. So the tangent line can be thought of as the limit of all the secant lines. So, all right, well, with that in mind, let's do some actual problems here. So the limit of a function can be thought of as the value of f of x as x gets closer to a specific value. So let's see if I can draw a picture here. Let's say that this is okay, so as x gets closer and closer to the 3, y gets closer and closer to 10. As x gets closer to 3 from the larger values, y gets closer to 10 from the larger values. Any way you look at it, as x approaches 3, and we're going to write that like this, by the way, y approaches 10. Okay, or write it like this. And so we say that 10 is the limit of f of x when x equals 3. Okay, so if we increase x from smaller numbers to 3, the function will continue to grow until it reaches 10. If we start with the higher numbers, as we keep reducing x down to 3, the function will shrink, and eventually it'll find itself here at the point 3 comma 10. So the formal language that we adopt here is that as x approaches 3, f of x or y approaches 10. So therefore the limit of f of x as x approaches 3 is 10. So for a smooth continuous function like this one, the limit is it couldn't be any easier because all you're doing is looking for the value of the function when x equals 3. So it might seem like, well, what are we doing here? It's pretty obvious that when x equals 3, y is 10. Why do we need to even think about a limit? Because in many cases, the function is a little bit more complicated than this. So let's look at a case where we have a problem. Here's the case. How about this one? Now you can see right away that the domain does not include 2. Because if x equals 2, we have division by 0. So what does this thing look like? Now this obviously came from Symbolab. What's happening here is that this function is actually a straight line, which is missing the point 2 comma 4. So there's a hole in the function. It's defined everywhere except there. But interestingly enough, in spite of this, as x increases, x goes to 2 in this direction, the function converges to 4. As x goes to 2 from this direction, the function shrinks until it eventually reaches 4. So in spite of the hole there, we say in this case that the limit is 4. And one more thing, I do want to mention, as far as the notation is concerned, when x is approaching 2 from the smaller values, we use a little negative here. And when x is approaching 2 from the larger values, we use a positive. And here we say, as x converges to, or approaches, I guess you're more likely to hear the word approaches. Hold on. They usually say from the left, meaning that we're starting with the smaller values and we're increasing up to 2. Over here, we say as x approaches to, as you can probably guess, from the right. So that little negative sign means from the left, positive means from the right. Either way, the function is getting closer and closer to 4. And so we say that in spite of that missing value there, the limit of the function is 4 as we approach 2. Now, of course, it's going to be different as we approach other values. In other words, the limit as x approaches -2 would be here. It would be 0. So in other words, there's going to be a different limit at every point on this function. So the way to think about it is that we're looking for the point at which what we're converging to. So so let's take a look at another case. Now this one is very strange. The one you're looking at now is not that strange. We're going to look at a very strange one right now. Oh no, we have an absolute value. That guarantees that this is going to be a messy problem. What does this thing look like? Oh my God. Well, wait till you see it. Well, now we have a real problem on our hands. We have two discontinuous sections of this function. As we approach from the left, oh, whoops, sorry, not -1, just negative. F of x is getting closer and closer to -1, which is right here, okay? Although it's right here. As we get closer to 2, we're approaching -1, because it's always -1 down here on this top section. As x approaches 2 from the right, f of x approaches +1. Well, now what do we do? Before, remember, the function approached 4 from both directions. So therefore, we concluded that the limit was 4. Okay, so it was, no matter what direction you're coming from, you're approaching the same point. So we say here that the limit is 4. It's different here, isn't it? Very different. It's like we're heading in different directions, so to speak. So here we say, you can express this in 2 ways. The limit diverges, or you can say the limit is undefined. It doesn't exist. There is no limit, because the point, the value that you're converging to, depends on which direction you're converging from, and they're not equal to each other. When that happens, we say the limit is undefined. Well, all right then. Now here's an interesting one. Following is a graph of y equals 1 over x minus 2 squared. Now we saw something similar to this earlier. Here's the Symbolab graph, and what do you notice about it? There's an asymptote where x equals 2. Of course there is, because setting this equal to 2 would give us division by 0. So just think about this. As x approaches 2 from the left, f of x gets bigger and bigger and bigger. And in fact, we say that it converges to infinity. There is no constant to which it converges. It keeps going up and up and up and up forever. And as we approach from the right, guess what? The same thing happens. As we get smaller and smaller, the function gets huge and eventually goes to infinity. So we have the same value that we converge to from both sides. So therefore, the conclusion to all this is that the limit of this function, as x approaches -2 to the from the left, is infinity. And the same thing is true here. And so our final conclusion is that the limit is just infinity. And if you notice here, it's written without a plus or a minus. This indicates that this is true from both directions. So when you see that, that is the actual limit of the function right here. We can have a limit from the left and the right, but this is what we define as the limit of the function at that point. So the limit can be infinity. Okay, because in a case like this, you can see why, because it has an asymptote. How do you like that? So what we're gonna see here at some point is we're gonna actually go through and define rules for calculating limits for specific cases. I just picked these at random because they show 3 different results. In the first case, we have a limit, worked out just fine. In the second case, we don't have a limit. And in the third case, we do have a limit, but it is infinity. So we're going to take a step back basically and define algebraically, how do you calculate limits? Now, it'll turn out to be actually a very straightforward process, but we could run into some very bizarre cases. And then when we do that, we have to know what to do about it. So the formal definition of a limit is this. The limit of this function f of x as x approaches a is L. Okay. Now, later on, not now, we're going to see a couple of ways of formally proving or defining this. We don't want to get too carried away with that. But we do want to understand what's going on behind the scenes here. So anyway, so this is what the definition of a limit looks like. And you can see x is the variable, f of x is a function of that. A is just some constant, and L is another constant, which can be positive or negative infinity. Okay, now, by the way, the limits, when we're taking limits from the left and the right, they have a special name. The ones from the left are, and the ones from the right for that matter, are referred to as one-sided limits. Okay, so this is the one from the left. You can tell because there's a negative. And this is an example of a one-sided limit. And then, of course, we came from the right as well. This is from the right because of the positive sign. And this is also an example of a one-sided limit. But the one we really care about ultimately is the so-called two-sided limit, which means the limit coming from either side is implied to be the same. So in other words, as long as the two are equal to each other, then the so-called two-side limit, or just the limit of the function, exists and equals the these two limits. Okay, so let's say they're both 4, like we had earlier. That means that the two-sided limit exists and it is equal to 4. If they're different from each other, then the two-sided limit is said to be undefined. And of course, we've already seen that limits can be negative and positive. All right. So why don't we look at a couple of special cases? There's always special cases to consider in calculus. For something like this, now remember we saw this earlier. Oh, by the way, I do want to point out that infinity and positive infinity mean the same thing. If we mean negative infinity, we'll put a little negative there, but we don't always use the positive and positive infinity. These represent the same thing. So we saw this before. Because there was an asymptote, that implied that as we approached the asymptote where x equals 2, that meant the limit was infinity because it's the same from the left and the right. But it turns out that the same thing would have been true if this exponent was 4 or 6 or 8 or 10 or whatever. As long as it was an even integer, positive even integer, we would have gotten the same result. Okay, in fact, why don't we demonstrate that with Symbolab? real fast. Let's try, let's get rid of that for a while. 1 over, and the constant doesn't matter, by the way. Let me try a different constant just so you can see it real fast. Hold on. I don't know what it was doing there. Let's try x minus 5 to the 6th power, just for the fun of it. Okay, so first we'll graph it. Oh, it's thinking. I guess we gave it a challenging one. Oh my God. Yeah, it's not that different from what we had, except for the values of the numbers. And then we can ask it for the limit of this as x approaches not infinity, but 5. And that should be infinity. Yeah, it's right there. Now, on the other hand, with a function like this, if this had been a positive but odd integer, then we would have had a problem, okay? Because it would have had a limit from the right would have been positive infinity, but the limit from the left would have been negative infinity, which indicates that the limit does not exist. Okay, so let me show you a quick example of this. 1 over x minus 2 to the 3rd. Now, you see this time we have 3 for the exponent instead of 2, which implies that we're going to run into this problem. So here's the graph. And you can see as x approaches 3 from the right, the function is increasing forever, which means that the limit is positive infinity. But as we approach from the left, the function is decreasing continuously, which means that the limit is negative infinity. And since those two are not equal to each other, that implies that the limit does not exist. Okay, so let's write this in here. Okay, and so since they're not equal to each other, the two-sided limit it does not exist. Okay. So what's coming next is all the rules. There's the so-called rules of limits. In other words, algebraically, there's several rules that we need to know, but it turns out that they're all very, very straightforward. Okay, there's very few surprises in here. And so we're going to go through these and we'll work out a bunch of examples. Let me just show you, for example, the first one, it couldn't be any simpler. The limit of a constant is just equal to that constant. Okay, there's no function at all. It's just a constant. So that's what it's equal to. And in fact, because you basically have a straight, remember with a constant, you have a vertical line. So, and then it gets a little more complicated as we go along. But we're going to introduce all these rules. And then we're going to get some practice with them. And then we're going to focus more on the strange cases that you might run into and strategies for solving for them. And then we can take a closer look at the more formal definitions and how limits are defined. And then we can move ahead to 3, which is maybe the most important chapter in the book, where we finally introduce the concept of derivatives. And we'll see that derivatives are themselves defined in terms of limits. Okay, so a lot of the results we use in calculus are based on derivatives. In fact, most of them, I would say. And so what we're going to see is how they're defined, and also learn all the rules of derivatives. And some of them can get quite messy. So Anyway, so this is where we're heading. And so, yeah, it's a little early, but I think we can stop right here so you can have time to recover. And then tomorrow, when we get back together again, we'll go through these rules of limits and we'll get some practice done. And then we'll move on to more complicated topics. All right. So, yeah, this was a little bit more abstract than usual. The trig functions, like I said, are important, but I didn't want to waste too much time with them so we can get to the good stuff. But later on, we will need the rules, the trig functions again. They'll show up when we're doing limits. They'll show up when we're doing derivatives. And so we can't just completely neglect them, but we don't need to spend all night with them either. So if you want to go back and read the rest of that section, there's a lot more discussion about identities and techniques for solving for trig functions. But if not, I mean, we have plenty of background now to carry on with this. All right, so if there's no last minute questions, I guess I'll just see you again tomorrow night, same time, same place. And I'll see you then.
Thank you.
Okay, you're welcome.
Thank you.
All right, good night.